Hello, glad I have you here. Today we are going to look at the closure data structures. Some key concepts about data structures. Data structures are readable, they are immutable. It means their value doesn't change. They have unique syntax such that you can differ them from the others. They behave like Minecraft blocks. The more you build your data structure, the better functions you need to have to interpret the data. Let's start with the first one. Nil is a possible value for any data type, and it stands for null, nullo, nothing, none, nada, niente. Nil is quite special. It describes an empty value, but you're going to find it everywhere. In Clojure, every function returns a value, and when there is no value to return, nil is returned instead. And we have numbers like long numbers, ratios, contagions, big integers, and big decimals. You have to remember that in Clojure, all numbers are typed as long until overflow. One is an integer in the other languages, but in Clojure it is a long number. Also numbers like this one, and with the function class you can see that this number is a long one. There are ratios. So we have like the numbers 1 divided by 2, so numerator 1, denominator 2, then we have 17 divided by 11, and with the function class we can see the type of the number. We have contagion, that is not actually a data structure, is a rule, and it means that some types are contagious. For example, an operation involving long numbers and big integers numbers results in a big integer number. An operation involving long and double results in a double. Let's look at an example. We have a long number, we have a double number, and here we have an operation between a long number and a double number. The results are a double number. A big integer is defined by putting an n at the end. As you can see, it's a big integer. A big decimal is a floating point big integer, and to define a big decimal, you have to put an m at the end of the number. The result is a big decimal number. Now let's have a look at some useful functions with numbers. For the basic operations, we have the addition, the subtraction, the multiplication, and the division. Let's see the results. And we can increment and decrement a number with the increment function and the decrement function. We also have comparison functions that tell us if a value is true or false. For example, is 2 greater than 3? False. Is minus 5 a negative number? True. We also have some functions that works with ratios. We can ask in this example which is the numerator of this ratio. Of course, it's 4. Let's look at one last example, the casting. So let's transform the 1.5, this floating number, in an integer. The result is 1, so we removed the 0.5 from the number. And with this, we conclude the section of the numbers data structure. Let's proceed with the strings. Those are the strings, are just a series of characters. As you can see, the letter L is a string, is not a character, and we will see the characters in the next section. But first, let's see some string functions. For example, we have the str function that just combines strings, and the string is added to this one and is joined with this number, and here there is no space, so I should have added a space before to get. Let's recompile it, and now we have a space here, and at last we have an operation with the addition function. Let's see at the comparator function. For example, we are asking if this ratio is a string, and is not, of course, because it's a ratio, and the string function returns as false. Most of the comparators functions have the question mark at the end. We have the characters data types, and to write a character you have to put a backslash at the start of the character. This /a is a character, and that's all about it. The booleans are very simple. They can have only two values, true or false. They are declared like any other programming language. False is a boolean, like that. Let's see the keywords. The keywords are not that easy because you don't see them in most of the languages. It's quite a new concept, but stay with me, it's not that hard. First, to declare a keyword, you have to put the colon at the beginning of the word. For example, colon red is a keyword. And what's cool about keywords? Keywords evaluate to themselves. What does it mean? When you call a keyword, they call themselves. So it's like they are both a value and a function. For example, when you reference a variable, you get the value inside that variable. But with keywords, the value is the keyword. Does it make sense? Example, I write here a keyword and I call it wine. And now I'm gonna compile this block. The value of wine is the keyword itself. This doesn't happen with a variable. For example, if I define a variable and I call it var and I put 1 inside here, when I'm going to call var here, it's going to say, hey, look, inside var there is 1. Okay? I hope that helps. With the keywords out of our way, let's look at the symbols. We previously called variables the one we defined with the def function, but in reality, in Clojure, there are no variables because we already said that Clojure has immutable data structures. While in the other languages, this operation is assigning a value to a variable, in Clojure is to define a symbol. The cool part of symbols in Clojure is that if we add code to them, they transform in expressions, but we are not going to look at those in this video. Let's have a look at some examples. Here we have 4 operations. The first one, we are defining the sum symbol and we are assigning to it the results of this addition. Then we have the hello symbol and we are assigning a string to it. And the last 2 operations, we are just calling the symbols to see what is inside. So as you can see, we defined the symbol sum, and here we defined the hello symbol. Here we call the sum symbol and we got the values inside it. Then we called hello and we got the value inside hello, that is a string. This user is just a namespace and we are not going to see in this video what a namespace is. The last thing you should remember about symbols is that they are not commonly used as variables. They serve different purposes and you have to look at them as identifiers for something else. And those are the collections. All of the Clojure collections are immutable and persistent. A persistent data structure always preserves the previous version of itself when it's modified. We're going to look at those in just a minute. The first collection, the most simple one, is a list. A list is a sequence collection and they are represented by parentheses. Insertion is efficient when added at the front. So, to represent a list inside Clojure, we have to add a quote at the beginning of this expression. When the interpreter finds a quote before a parenthesis, it understands that what is next, it is a data structure and not a function. If we remove the quote, 2 is going to be interpreted as a function. This is going to be interpreted as a list of values. It's good to understand that in Clojure, every piece of code is a list. That's why we have parentheses between functions. We have to distinguish a list data structure from a function. Let's look at some functions that we can use with list. So the first one is count and is a function that counts the elements inside a list. We have a 2, a character, another number, we have a string here, and all these counts to 4. Then we have the conj function. It's used to add elements to the list. Conj always add the new element at the front of the list, that the insertion is efficient when adding to the front. The vector is an indexed collection starting at 0. Insertion is efficient when adding at the end, as opposite to list. To define a vector, you have to write inside brackets, like this. Those are some functions that we can use with vectors. The get function gets as first the vector and then the index of one item from the vector. In this case, if we compile this, we see that we get blue from the vector. The second function is conj, and it works similar to the list conj. The difference is that the list you add at the front of the list, and in the vector you add at the end of the vector. In this case, we add 7 at the end of the vector. You can see the result right here. The third function is assoc, and is a function to modify an existent vector. For example, we want to change the index of the value 1 to change red with the word and we do it like so. We pass the index of the value red, which is 1, and the new string. The results are black and yellow, and that's it for the vectors. The maps is just a collection of keys paired to values. For example, we have the key x that is paired to the value 12. We have the key y that is paired to the value 2, and so on. To understand which one are maps, you have to see that are displayed inside curly brackets. We have two different maps: the hash map and the sorted map. The hash map is the default one, and the sorted map is, just as the word suggests, a sorted version of the hash map. To understand the maps better, let's have a look at some functions we can use with maps. The first function, the one that we use to create a hash map, is hash map, and we have to pass keys and values like this. We pass the key and the value, a key and a value, etc. To create a sorted map is just the same, but this time we are going to use the function sorted map. Now let's see the get function. The get function, similar to the vectors and the list get, is the one that gets you the value from the map. So let's compile this block and see that if we pass to get the key y, then we get the value 2, because 2 is the value of y. Another function is vols. Vols serves to get all the values, but not the keys. We get all the values from the keys inside a list. Remember, the parentheses are to indicate a list. For the last function, we are going to see dssoc. Dssoc serves to remove a key and a value from the map. Here, we are passing to dssoc the map and the key we want to remove. In this case, we are going to remove the z key and the value from z. And here is the map with only 2 elements. The last data structure we are going to see today are the sets. The set is a collection of unique values. Every value inside the set cannot be duplicated. They can be either hash set or a sorted set, and the values of the hash set won't display in order you define them. That is because of the internal mechanism of the sets function. It's important to understand that the set is not a combination of keys and values, and all the elements from the set are standalone. The sets are defined by adding the elements inside curly brackets and a char at the front. Now let's see some functions that we can use with sets. To create a hash set, we're going to use the function hash set. To create a sorted set, we have to use the function sorted set. And what's the difference between those?
The hash set are not represented in the same way as they were declared. Instead, in a sorted set, elements are sorted based on type, in this case alphabetically ordered.
Those duplicated B's and C's are getting removed. Another function that we can use with sets is conj. We have to pass the set and the element we want to add. In this case, the element is added
to the set.
With sets, we can also use the function get to get an element from the set. I'm trying to get the element A from this sorted set and results in A. This is everything about Clojure data structures. I hope it helped. And if you want to help me out, subscribe, like, and comment, and see you in the next video.